Welcome to this explainer brought to you by Forge College. Today, we're diving straight into error handling and security awareness in transactions. Now, to give you some context, we're navigating the Solana development tools track, specifically looking at interacting with the Solana network within the Building with Solana kit, which some of you probably know as Web3.js. Look, if you're building in Web3, you are going to hit errors. It's just a fact of life. But instead of letting a giant wall of red text completely ruin your day, we're going to put on our detective hats and jump right into our very own CSI-style debugging lab.
Ah, yes. It worked on my machine. Until it didn't. The famous last words of literally every developer. In our previous lesson on programmatic transaction building and inspection, you successfully built out those transactions. You attached the signers, shipped them to the cluster, and everything was pristine. But as we all know, moving those perfectly controlled transactions into the wild of real-world applications means failures are absolutely inevitable. We just need to know how to handle them without panicking, and more importantly, without putting our users at risk.
So what actually happens when your Solana transaction fails and throws that terrifying wall of red text in your terminal? How do you track down the real culprit? Well, instead of seeing this as a total disaster, or just furiously mashing the retry button and praying for a different result, we're going to treat this failure as a crime scene. Every error leaves a trail of clues, and we just need to analyze it systematically.
Okay, here is our investigation blueprint. We've got 1. The scene of the crime, 2. Reproducing the failure, 3. Examining the evidence, 4. The usual suspects, 5. Closing the case safely, and finally, 6. Review and next steps. Let's get to it.
Step 1. The scene of the crime. Classifying the incident. Because hey, the very first step at any scene is figuring out exactly what type of situation we're dealing with.
In the Web3 world, we're basically dealing with two distinct categories of errors. First, you've got your transient errors. These are just temporary network hiccups. Maybe you've got a stale block hash because your submission was a tiny bit late. For these, an automatic retry is totally justified. But then, you have deterministic errors. These are fundamental, undeniable flaws in your logic, like a completely missing signer or an uninitialized account. Retrying a deterministic error is literally like repeatedly pushing a pull door. It's just never going to work. You have to go in and fundamentally fix your code or the application state.
Moving on to step 2, reproducing the failure, the reenactment. To actually solve the crime, we have to recreate it.
This right here is the golden rule of debugging. It's a simple 4-step mantra. Reproduce, diagnose, fix, verify. You're going to repeat this cycle until your transaction finally reaches a confirmed status. But listen, here is the catch. You must recreate the crime in a controlled, isolated environment. Think the Solana DevNet or a local test validator. Never, ever test your failing transactions on mainnet with real funds. We want a nice, safe sandbox where we can trigger that failure on demand.
Step 3. Examining the evidence, logs, and diagnostics. Once we can actually reproduce the error predictably, it's time to gather clues using our programmatic logs and the Solana CLI cross-checks. Think of the RPC error response, specifically tx.meta.error, as your initial coroner's report. It gives us the high-level reason the network rejected the submission right out of the gate. So if a signature was missing or an account didn't have the right authorization, meta.error is going to tell you. It's the broad stroke, the immediate cause of death for your transaction.
But, sometimes that coroner's report just isn't enough. Sometimes the transaction makes it past those initial checks and dies deep inside the smart contract. That's when we turn to tx.meta.log messages. These program logs are basically your detailed witness testimony. They reveal exactly what panicked inside the contract, step by step. If there was a runtime error or some custom program error, this is exactly where you'll find the smoking gun.
Step 4. The usual suspects, the lineup. We've collected our evidence, so let's take a look at the most common culprits you're going to encounter on the tricky streets of Web3.
This is essentially your rap sheet for matching clues to suspects. See, signature verification failed? Your suspect is almost certainly a missing signer, or maybe you just put your signers in the wrong order. Seeing panicked in your program logs? You're likely dealing with a program runtime error. What about compute budget exceeded? Well, your transaction simply tried to do way too much heavy lifting and ran out of gas. And if you get a block hash not found, that's just a transient error. Your block hash went stale, so fetch a new one and try again. Knowing how to match these specific clues to their suspect is going to save you hours of aimless wandering in your code base.
Which brings us to step 5,
closing the case safely with proper security protocols. Because knowing how to fix the bug is really only half the battle, we absolutely have to do it securely.
Sloppy key management is a developer's worst nightmare. While debugging, we have to follow strict safety rules. Treat your private keys like highly sensitive, radioactive evidence. Isolate them completely. When you're testing, only use disposable, ephemeral test keys. If you accidentally leak an ephemeral key on DevNest, who cares? No big deal. But if you log a raw private key from your mainnet wallet to the console while trying to debug a missing signer, yeah, you're going to have a really bad time. Keep those debug key pairs out of your version control by aggressively using your .gitignore file.
Finally, Step 6, Review and Next Steps, compiling the debug report. You've reproduced the error, examined the evidence, found the suspect, and applied a safe fix. Now we put together the case file.
A complete evidence bundle proves beyond a shadow of a doubt that you actually solved the problem. This report should include your raw failure output, your diagnostic evidence from the logs, a clear root cause statement, and your post-fix confirmation logs. Having this documentation isn't just busy work, I promise. It is an incredibly valuable asset for peer review and honestly for your future self when this exact same bug pops up 6 months from now.
And case closed. The ultimate victory in our investigation is passing that deterministic test, running your code, and seeing meta.err return as strictly null in the terminal. You cross-reference that with the Solana CLI, and it proudly marks your signature as confirmed. There really is no better feeling of absolute triumph in Web3 development.
So, how do we take these micro-level debugging skills and apply them to a massive, macro-level application? Well, now that you can investigate and resolve individual transaction failures like a seasoned pro, you are perfectly primed for our next lesson. We'll be doing a comprehensive overview of dApp architecture, where we dive into things like idempotency, state management, and really robust retry policies.
Thank you for putting on your detective hat and investigating with us today. Learning to embrace errors as useful data rather than roadblocks is an absolute superpower. Keep investigating and building resiliently. And be sure to visit forge.college to learn way more about this subject, access full courses, and dive deeper into other incredible Web3 topics. But before you go, ask yourself this. If your code failed in front of 1 million users tomorrow, is your debugging process actually resilient enough to catch the culprit before the funds are gone? Think about it. See you in the next one.